Okay, welcome back everyone. In this video, I'm just going to do a quick example of how to solve simple harmonic motion problems with energy. And this is actually number 26 from page 461. So we start off with a ball with a mass of 250 grams, and it is located 10 centimeters or 0.100 meters above the top of a spring. It has a spring constant of 60 newtons per meter. And so what's going to happen is it will fall and compress the spring a certain amount from the starting point. So if I make this the starting point, it will compress the spring a certain amount x, and the ball will be there. Okay, so we need to figure out what distance does the ball compress the spring. And so we're looking at a situation where there's actually two different types of kinetic energy that two different types of potential energy that we're dealing with here. We have potential energy due to gravity, and we also have potential energy due to the spring. So the way that we're going to set it up is kind of like this. Well, let's think about if the total energy that we start with is equal to the total energy that we end with, what kind of energy are we starting with? Well, when the ball's just kind of hanging out up here, we're talking about potential energy due to gravity. That's all that it has. The spring is not stretched and it's not moving, so that's the only energy that we have. And then afterwards, so V initial is 0. Afterwards, V final is 0. The ball has compressed the spring as much as we can, and so we just need to find the distance x that it's been compressed. There is going to be spring potential energy, so potential energy due to the spring, but if we are careful in the way we set this up, we can get rid of gravitational potential energy. And here's the key. You always have to have a 0 point for gravitational potential energy. I'm going to make the 0 point basically the second point where the ball comes to rest. So the true height that it starts from is not 0.1 meters, it's 0.1 plus x. That's the initial height. And so therefore the final height is going to be 0 because we're making this h equals 0 line right here. So hopefully that makes sense. And the neat thing about potential energy is that we can do this. We can set the 0 point anywhere we like. So what this means is that the expression for gravitational potential energy is going to be mgh initial. And that's going to be equal to 1/2 kx squared. So we plug in that h initial is actually 0.1 plus x, and then on the other side we have 1/2 kx squared. Alright, so now we need to distribute and kind of see what's going on here. So mg times 0.1, okay, turns out to be 0.245. I'm going to leave units off for now. And then we're going to add mgx. Okay, so I've distributed my mg to both terms, and then that's going to be equal to 1/2 k, which is given to us as 60, so 30 x squared. So believe it or not, we actually have a quadratic that we need to solve. So I prefer putting all of the terms on the same side, and it turns out that mg is 2.45, so this middle term turns into negative 2.45x and then 0.245 because mass is 0.250 kilograms and g is 9.8, so mg is 2.45. Okay, so now we just pop this into quadratic equation, and if I do this too fast, just pause or rewind. That's a great thing about videos. So it's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And this actually gives us two possible answers. We get x is equal to 2.45 plus or minus, it actually works out pretty nice, 5.95 over 60. And we actually have to add them together for this. That's the only one that works. We can't get a negative number for x because what that says is that the spring is actually extended up. And that doesn't really make sense for this situation. Okay, so we're going to conclude that x has to be equal to 0.14 meters. And that, in fact, is the correct answer. Okay, so that's part A. Part B is predicting, well, after it hits the spring and stops, how high will it bounce up again? How much is the rebound? And because we know that energy is conserved, and because we know that there's no friction or air resistance or anything of that sort that in real life would be affecting it, we can just write down immediately that the final height after rebound is going to be 10 centimeters. So it'll just go back to the same exact spot. And if there's no friction, it'll oscillate back and forth indefinitely. Okay, so that's one example of how to use energy in simple harmonic motion. And this actually focused a little bit on including gravity in it as well.